Hello and welcome to the Engineering Dynamics Course Companion. This is class 19. We're dealing with the kinetics of rigid bodies, or at least the lead up into the kinetics of rigid bodies, covering the mass moment of inertia. My name is Newt Dog, and this is my buddy Wormy, and we are your course companions. As always, you can skip ahead to the example in the link below in the description. So first, we'll start out with the bottom line up front. There's a lot of words here. Kinetics of rigid bodies involves both translation and rotational influences, right? And one of those rotational influences is the mass moment of inertia. That is the resistance of a body to rotate. Just like mass is the inertial resistance to translational acceleration, something that has a size and a shape to it that's prone to resist rotating. It's the mass moment of inertia that wants to resist its angular acceleration getting started. And we'll start using that in the next class and a couple after that. Something we need to know is the center of mass. That's the location where it's going to be easiest to rotate the thing and therefore have the smallest mass moment of inertia. So often we want to find the center of mass of a piece. The mass moment of inertia resists rotational acceleration, I've said, just like mass resists translational acceleration. And the mass moment of inertia kind of describes how the mass in a rigid body is distributed. And it's the further it gets out away from the center about which it's rotating, the much more influence it has because it's by the square of the distance. And it's very similar to the area moment of inertia that you will have covered in statics perhaps, or in mechanics of materials. It's like we're dealing with the mass moment of inertia, whereas that deals with the area moment of inertia. Used in totally different ways, but they are kind of similar in concepts. Because we also need the parallel axis theorem, which is also used in the area moment of inertia. And we use that when we want to transfer from one point of rotation to another point of rotation. We should always use the center of mass as the go-between if we're going to go from places, and recognize that the center of mass is going to be where it's the smallest. So if we want to move it from the center of mass to someplace else, we need to add in a mass times the distance get moved. But if we're going to move it from some other place to the center of mass, we would subtract out the mass times the distance that it has to move. And it's very convenient sometimes to do this in a table, by the way. I don't think I included it in here, but there's also a term called a radius of gyration, which is a nice way to summarize the mass moment of inertia compared how the mass moment of inertia compares to the overall mass. Okay, so center of mass is something that we want to do first most of the time when we're trying to doing an analysis of a body and trying to, as we're preparing to try to do a kinetic analysis on a rigid body. So that's to find that, what we do is we take what we could think of as this moment of a mass, and we sum all of them up and then divide by the total mass. So if it's some weird shaped thing right there, right, we would take some reference right here of an X and a Y, and we would take little individual mass pieces right here, DMs, and we would find the position of the thing, all the individual Y's and all the individual X's, and we would integrate them, and then also probably integrate all the masses to get that. We could also find this by pieces. So the above one, when we're integrating it, it's some weird shape that has like maybe some functions, but also a lot of times we will have a table, or we always will have a table that has for different types of shapes, like circles or cylinders, I should say, or rectangles or parallel pipette blocks, various things, and you can add and subtract them from each other and then figure out where that mass moment of inertia is going to be. We could also, by the way, we should recognize that there could be a rate. Sometimes we'll want to know the radial distance from a reference point as well. So just recognize that we have that there. And here's a picture of me turning if I just would wanted to have it for some reason, I have a crank that's trying to spin the boomerang around its center of mass. Noteworthy, if we want to try to find that boomerang and try to find its center of mass, one way that we could approach it would be to take this total rectangle that we could draw around the thing, and then we could subtract out the individual triangles right there, and that would get me this mass, the center of mass right in there. We're going to use that. We could use that same technique in the mass moment of inertia. Now, mass moment of inertia, conceptually, it's easy to think of it in terms of like sitting in a chair and spinning, right? And just like an ice skater, if you've ever seen maybe ice skating, where they hold their hands out wide and then do a spin, and then they tuck them in, right? And when they tuck them in, what they're doing is they're decreasing the mass moment inertia. When you have your arms out wide, your mass moment inertia is larger, right? And so when you bring it in, it's smaller. So what they do is they're demonstrating actually the conservation of angular momentum when ice skater would spin with their arms out and then bring them in, and then they start spinning quicker because the angular momentum is conserved, and so they have the same angular momentum, but because they have the mass moment inertia gets smaller, their angular velocity increases, right? So the definition of mass moment inertia I is going to be that the distance from the axis of rotation squared times dm, right? And that could be, it could be the z that we could be taking a look at, or x, or, and by the way, this is for like maybe a cylindrical piece that we might be looking at right here, right? So this might be like this distance right there. It could be like r that we're dealing with right there. Okay, but anyway, I digress. So here you go. This is about the, I should say cylindrical piece. Maybe I should go back and erase that. I'll leave it on. So here's for the boomerang, right? So this boomerang right here, it could be spinning about this axis, but it could also spin about the x. It could also spin about the y, right? So we want to, so here's how that mass is distributed, and you can try to think about which way it's going to be easiest to spin. It's probably, for this one, it's probably going to be easiest to spin about the z-axis. Here's some common shapes and the mass moment of inertia for about each of these axes. Now, most of the time for these, typically we're going to, for some body that we want to know, we'll probably want to go around the z-axis, but you could, think about this guy as like maybe this would be similar to like a baton, right? And so here's a solid piece. And if you're going about the z, you're coming about that axis right there. But if you're going about the, let's say the x-axis, it's going this way right here. It's going about the y. It's spinning this way right here. And then you could see that, like, if it gets a little bit larger right here, right, in terms of the radius of this thing, right, if it gets fatter, that radius will be influenced by so the mass moment of inertia about that axis and about this axis will have an additional term here. Notably, these are the same terms right here, right? And you could even check out for a disk, it's the same. And a similar thing here, right, about the z-axis. Then they're identical for this rectangle versus this block, but this right here is actually, and this right here is actually looks very similar to these, right? So like when it's long and thin about the thing, it doesn't matter how deep the thing is when it's spinning. So there's other pieces and other shapes that you might want to look up in other references, but here are some basic ones. And by using these basic shapes, you can often generate the other mass moment of inertias, or the mass moment of inertia of a more complicated piece, right? All right, so one of the things that you want to learn how to do is to move on the axis about which something is rotating, change it to a different reference. So we use the parallel axis theorem, which looks like this. And it's very similar to what you use in the area moment of inertia in the other classes. And we're using I bar to mean the mass moment of inertia about the center of mass, right? So here's the difference right here, right? So here it's spinning about the center of mass. Here it'd be spinning at a point that's away from the center of mass. You could just imagine that it's going to be harder. Like if it was this, if we're spinning it about this axis, it's much easier because this is the center of mass right here. But if you're spinning it about this axis right here, right? If you're spinning it about the end of the thing, much more difficult than spinning it right here. And in order to find the resistance, that moment of inertia, you need to translate from here to right here. So here would be the distance, and here that's calling it d. This distance squared times the total mass of the thing would give us the mass moment of inertia. So here is like the idea. Here's about the different axes, but here's a more difficult one to spin it about, right? So I want to make a comparison between spinning it about this. That's just like what's being done up above, right? Being spun about the center of mass, or being spun about an end right here. Or this right here being spun by this little axe right here, as opposed to being spun and coming around like that right there. And the same thing from here, being spun here or being spun right in there. So hopefully you'll get those idea of those of that orientation. So here's example out of chapter 19. I call this example 19.4. Where we want to get the mass moment of inertia and the radius of gyration, which, by the way, the radius of gyration, we could call this like R. I think I give it a subscript. But anyway, the radius of gyration can be found from I, the square root of I divided by M, right there, right? Or we could say that I is equal to R squared M, where R is a particular thing. Sometimes I call it RG. Some people call it K. I'm not sure which one. We'll see later what I put that in. But let's see, and we want to find both the mass moment of inertia and the radius of gyration of the plastic part with respect to the z-axis, and for the z-axis, and through the z-axis, that's the axis that's parallel to the z-axis that passes through the center of mass. So we need to find the center of mass first to be able to do that. And they give us the density of the plastic, and they also give us all these dimensions, right? So this thing's huge. It's like 1 meter by 1 meter, half a meter, 0.125 is the diameter of that. All right. So what we want to do, our strategy is to break this thing down into blocks, right? So we could do this in a number of different ways. We could also have a big square and subtract out this little square up at the top. But I chose to take a rectangle and a square, add them together, and then subtract out the circle. So I figure out what the masses are of each of these pieces by taking the volume of the piece, and I'm calling this one point one, this part 1, this part 2, and then this part 3. So that's what all the subscripts are. So this is just base times height times thickness, and I have, of course, times density. And then I'm able to get the mass of that, and mass of 0.2, similar, but we have different dimensions. And then for the mass of the little cylinder that's going to end up being subtracted is right there. Yes. So, and right here, by the way, I took area and multiplied it by the length of the thing, and that's, or I should say, the thickness through the piece, right? And it does say somewhere where how thick the thing is, right? I should have. I guess I didn't. I should have given that dimension right in there somewhere. I didn't. Okay. Oops, my bad. So that dimension is 0.5. Okay, so we figure out what the total mass of this is by taking the rectangle and the square, adding them and subtracting out the cylinder. And it's a good idea to, we'll use the bottom left corner right here. That's just a good place. And when we're looking for the center of mass, it doesn't actually matter where we take the reference, just as long as that when we give the answer, that's what we say it is. So we take the sum of the centers, right? The sum of the centers times each of the mass divided by the total mass, right? So this mass, this 250 right there, it's located at 0.25, right? Because it's oh, wait a minute. Oh boy, did I get that wrong? 1.5. Why does I have that was 1.5? This should be, right? That's wrong right there. That's wrong. These are all wrong. That's wrong. And sure enough, that's wrong right there too. So got to be careful. Got to be careful with these things. 0.75. Yeah. Well, I made some mistakes in this one, huh? That's easy to do. You have to keep track of this stuff, right? So you got 250, and that should be multiplied by this should be 0.5 right here. I know I checked this, so that's a little disappointing here. That should be, oh, you know what? Up above, I think this right here doesn't match with this right here. I think that's what's happening right here. Because, okay, so what I actually did was this right here. Yeah. Okay, so this diagram up above is not what I actually did. What I did was I took this distance right here and this distance right here, okay? So this is the 0.25, right? So that's going to be that distance right here. And then this is going to be the 0.75, which is going to be from this, like I said, I did that right there. It's going to be from that to right here to that right there. And then I'm going to subtract out that this mass right here times that distance as well right there. Okay. And anyway, I divide by the total, and I get this, right? So that's why I got the right number, but I made the diagram incorrect, or I made this equation incorrect for the diagram, either way. You could also see for the in the y direction, something similar. I'm sure I made the consistent mistake, where I take 0.5, right? So that's going to be that distance right in there. And I take 0.25, which is going to be that distance right here. And I do this, I use that both at 0.25 also for the circle, right? That's the distance. And I get what that the center is going to be. And it's a good idea to try to like take a look at it and in the context of where that thing is going to be located. Now, right here is 0.5 and 0.5, whereas this is going to be down and to the left of that center. This works well to do this in a table form, right? And so even up above, like this is actually drawn correctly, whereas that is drawn incorrectly. Oops, sorry. All right, so the computer is slowing down. All right, so this lends itself to doing it in a table, right? And so where I have the position in the x direction, I have the dimension in the x direction, either the radius or the x direction. That's what I decided to use here, just to keep it the thing the same. I have the y dimension and then the z dimension. And then I also have the distance for each of these pieces from the x direction, from the y direction, and then from the z. The z isn't really necessary because this thing all has the same thickness to it. So we're hoping we could be able just to guess what the center of mass is in the z direction. But we find the volume here where we just multiply the x, y, and z by each other. But then on the one down below, we make sure that we do this as a cylinder, right? Where we take the area and multiply it by the dimension in the z direction. Then we multiply this by the density, and we can get the mass of each of the pieces. And then we could take this mass, multiply it by this dx, and so we get the m dx. And the same thing, take the mass, multiply it by the dy, and then just to be thorough, mass times dz right here. And then, so we do those for each of those, and we get the total right here. We also get the total mass. And then here, we just divide this value by the total mass, and then this value by the total mass to get that, and then this value by the total mass, and we get the expected 0.25. Right? So making a table out of this is very convenient, especially if we're going to make something in Excel, right? A spreadsheet. Now we know the center of mass is right there. So that was our first thing, and we knew what the masses were from either from the table or by doing it individually. So what we want to do is we could write out one long equation to try to find the mass moment inertia about this guy right here. And what we want to do is we want to take, first off, we take the mass moment of inertia here about this axis for 1. And then, so we find that, and then we take the mass of 1, and maybe I'm going to use another color right here. I don't want to use orange because the thing is orange. So we want to take this distance right there, right? So it's going to move from the center of this piece right here, and it's going to move down. So that's what that D1 is going to be. For right here, we want to find the, and I'll draw it like this way right here. Here's the axis about which that 2 is going to be rotating. So we find the mass moment inertia of that block, and then we move it by D2. So like, see, I will use this light blue right here. So it's going to be moved like that right there. That distance is going to be that D2. And then we need to subtract out that cylinder, but we need to subtract out the whole thing. So first we have to add together what the what that cylinder is going to be, and that's along the same axis as that part is the block 2 is going to be. And then we move it and we subtract the thing out. So right here I've already drawn the thing out. There's what the D1 and the D2 are going to look like. So what we want to do here is we find the mass moment of inertia for a block. We could go all the way back to the thing, or we could look it up right here. Because I guess I'll just go back. Let's see. There you go. So for a block, and you can see it's about any of these axes right there. It's going to be 1/12 mass times one dimension squared plus the other dimension squared, right? It's going to be, so let's take a look at this one. It's going to be height squared and base squared, right? Or you take a look at this guy right here, and it's going to be this squared times this squared, right? So it's the ones that it's perpendicular to. These are good ones to try to like memorize the mass moment inertias, at least for a block and a circle or a cylinder, I should say. You notice that you notice the 1/12 shows up in the thing. So anyway, here is so here's 3 parts right here. Okay, so here is that 1/12 mass times the dimensions of that rectangle. But then here's also that mass of the rectangle, and then here is the D1 right here of the thing. That's the distance of that thing squared. And then right here, here's for the little square block. That's this guy right here. Here's his mass moment of inertia, and then you add the mass of it times that distance squared. So it's going to be this squared. And it's kind of funny, but as I drawn it, I have the square root of it, and then it's squared. So, but I just want to emphasize that we're finding that diagonal distance and then squaring it. And then lastly, we have, you'll notice that 1/2 m radius squared. And that should be radius squared right there. And I'm a little concerned that I accidentally put in the diameter to the thing. I might have made a mistake on that. And then the mass of it, and then its distance, moving the thing. And then once they're all at about a common axis, then you can add or subtract them together. And here's what we get for the mass moment inertia. And now that we have that mass moment inertia, that's going to be about the corner. That would be about the same thing as like if this is a rectangle, it's about like it's spinning about this axis right here. But it's going to be easier to spin it right here. Like if we were going to spin the book, about this way, it'd be harder. We'd have to have like some kind of rod, and it'd be fixed onto the thing to allow it and to force it to spin about there. But that would be the more difficult to do about something that's a non-centroid. But here's the radius of gyration. It's the summary kind of how the mass is distributed, because you take the mass moment inertia divided by the mass and take the square root of it. And so this is like, you almost think of it like an average location of that mass for that shape of the thing. Now, if you want to get the mass moment of inertia and move it to about this other axis to the center of gravity, you need to make sure that you recognize that it's going to be smaller. So what we do is we take the mass moment of inertia that we just found, and we subtract out the mass times the distance. Right, so there's going to be that distance right there, which is x bar squared plus y bar squared. Now, once again, by the way, you could have also said the square root of that, but then squared it, right? So that's why we're not showing either the square or the square root of the thing. And you end up finding that you get 55.44 kilograms meter squared, which is the units right here. We have mass times a distance squared. So in U.S. units, it would be slug feet squared would be the typical thing that we would get. And then the radius of gyration, we could see that it's going to be smaller here for something that's about the center of mass. A convenient way to approach this is to make a table out of it. Once again, doing something in a spreadsheet. You could make an extra long table where you do the centroid, or excuse me, the center of mass and the mass moment of inertia all in one big table. That's useful. It sometimes is hard to present on a single page right here, so I did it in sections here. But you have like the basic dimensions and the mass, and you're able to get the individual mass moment of inertia about the local center of mass, and then you're able to find. Then you have the distances that it needs to move in the x direction and the y direction, and now we have the total distance, like that each one needs to move to get to the thing. And then you could find the parallel axis theorem of the individual things, and then you can add them up together or subtract out the cylinder for the whole. And then we also can find the distance that we need to move. This is really the x bar squared plus y, the square root of x bar squared plus y bar squared. And then you could use the parallel axis theory, but to subtract it out to get to move to the new place. All right, so there's an example. There's a very useful thing. Commonly, it's a common task that you have to do. So for more examples, check out the Engineering Dynamics Course Companion, Parts 1 and 2. These are published by Morgan and Claypool, and they're available on Amazon, or you can follow the links below to go to the Morgan and Claypool Publishers website. Please consider subscribing to this channel. I'll be adding more content as things progress, and hopefully this will be very helpful to you. Please provide some comments, some feedback, and thank you very much.